And this is the kind of thing that we do. We study the physics and properties and dynamics of the oceans, and because the oceans have a huge capacity to store heat and interact with the atmosphere, we study how the oceans interact with the atmosphere. And Andy already made reference to this, but I'm going to skip through a few slides. The sorts of things I look at are climate modes of variability, and Andy alluded to this, but each of these large-scale processes, at the core of these processes are fundamental geophysical fluid dynamics processes that we need to understand very, very deeply to make progress on these complex systems, whether they're in the ocean or the atmosphere. I look at the global ocean thermohaline overturning circulation in some work as well, and right up to the high latitudes. And I'll just skip down to a separate slide altogether, just to focus on this ocean thermohaline circulation. So this is depth here versus latitude. And in some sense, when you go back to the observations made almost 100 years ago now, Voost has a lovely section across the Atlantic Ocean that shows the high saline water from the North Atlantic flowing over the shelves and so on in the North Atlantic sector and exiting into the Southern Ocean, being upwelled in the Southern Ocean, abyssal water flowing off Antarctica and other things happening in the tropics. When that diagram came out, it was kind of easy to see where all the water masses were going to. Salinity is conserved in the oceans, and you could make sense of this at its larger scale. But if you really need to understand this part of the climate system you need to actually understand a whole heap of processes. You need to understand the generation of internal waves, for example, and their breaking and their mixing in the interior. And this happens when tides agitate across a rough bathymetry at the seafloor. You need to understand even lee waves. When water masses flow over rough bathymetry, they can generate lee waves. You need to understand gravity currents. I know there's a lecture on this very late in the week. You need to understand convective overturn and a whole bunch of processes like mixing across isopycnal surfaces or across density surfaces and mixing along density surfaces. The list goes on and on. It's a GFD problem that we have. The oceans are basically, and the atmosphere is a very thin layer of fluid on a rotating sphere. And it's actually a physics problem to understand this. And it requires, the good thing is we've got a whole bunch of equations that govern the dynamics of these media, and I'll talk about those in a second. And we've got equations for momentum in 3 dimensions, conservation of mass, conservation of energy. There are state equations for temperature and salinity and so on, and how they relate to density. So we have lots of equations, and they're governed by fundamental laws of physics. And so we have a system that's reasonably well constrained, but lots of subgrid scale processes that make our jobs tough. And it gets even more complicated when you get up against the continent and start talking about interactions with ice and so on. Having said it's very complicated, I would come back and just say that there's also a real place for simplified approaches to the system. And I just throw this one up here because it's still on this idea of the ocean's thermohaline circulation. And at its largest scale, you could construct some kind of simple analytical 2-box model or another simplified model of this system where the oceans are gaining heat at the tropics, and gravity is trying to flatten out this density gradient that's created. So there's more heat coming in here than at high latitude. So if gravity has its way, it would tend to put that surface warm water as a thin, uniform film of water right across the global ocean. And in contrast, the sun's continually trying to create this density gradient. So gravity's trying to remove the density gradient, the horizontal density gradient, and the sun's trying to create it. And in its largest sense, you could start to model this system just by incorporating some mixing at depth to remove the density that you're pumping into the interior and create an overturning circulation. So there are some lovely papers that you see in the literature where, despite the complexity of all of the individual processes I just described, you can go and simplify the system. And I think part of going to the lab this week, you'll look at individual processes, but there are some times where you can try to simplify the system you're looking at its larger scales. Okay, that was the sort of preamble to this lecture that now is the introduction one. And it's going to be some of the basics, and these equations will come back, and these concepts will come back through many of the lectures that I see are on offer this week. And I'm just going to go towards the end of the primer, you've all read the primer, right? And I looked across I know half of you and I know half of where you've come from in terms of your academic backgrounds. And so I'm guessing that there are people who look at this and get overwhelmed by all those symbols and notation. And there are other people that go, yeah, that's fine, I've seen it all before. So there's lots of symbols here, but there are concepts that are actually relative. This is shorthand. I could have written this whole equation set out with words, actually. So, but words get very long. And we've got some shorthand here. So here are the rotation forces. This is the acceleration terms, so the nonlinear terms and also the local acceleration in time. Over here, there are pressure gradient terms. I'm going to come back to those a lot this lecture. And there are frictional forces here at the end, and I'll come back to those at the very end, just with the vertical friction of the wind over the ocean. So this looks like a lot, but really there's just three different dimensions. So this is the east-west sense, the north-south sense, and then the vertical sense. And it turns out that for many flows, we don't need all of these terms. Many flows in the ocean and the atmosphere occur slow enough in time or long enough in space that many of these terms are negligibly small compared to other terms. And that's going to be, a lot of this lecture actually is going to be about starting with these equations, working out that in a certain scenario we can drop most of the terms, and then looking at the resulting balance in more detail. So from all the primer document, which I think is about 8 or so pages or 7, lots of symbols and lots of equations. These are the two key that I'll use a lot this lecture. This second one is that's just the material derivative of the flow. So these terms here could be written in much shorter hand notation. The second concept that I'll use a fair bit is just the conservation of mass. And so written in its full gory detail here, but apart from sound waves in the ocean, it's this assumption that the fluid's incompressible is a good one. And so you just get that, effectively think about a box, the flow in and out of a box is sort of basically balanced. So if you think about a parcel of water or a parcel of air, then any gradient of U across that box or V into the box or W, let's have vertical going up, any gradients in U, V and W across that parcel must be balanced. So you're not creating mass in any way. Okay, so they're the two main bits of the primer that you'll need to know. And to make some progress with these equations, I just want to point out, and this is impossible to see from the back of the room, I'm sure, but it's important to think about what we do with the ocean or the atmosphere is we think about the processes we're interested in. So whether it's internal waves or tides or eddies or large-scale gyres in the ocean, weather patterns in the atmosphere or mountain waves, sea breezes and so on. All of these processes have some characteristic length scale and a characteristic velocity scale. And so we can go to the equations I had previously and start to tease out what terms in those equations might matter. And of course, they also have a characteristic time scale. Velocity is length divided by time. So you can link these three scales together. And so whether you're at these they generally sit on this sort of part of the axis. So generally the shorter the time scale, the smaller the space scale, and generally, obviously the larger the space scales, the longer the time scale. What makes the system so complicated is that there's interactions there's a cascade of energy right along these processes here. So very small scale turbulence actually drives the global thermohaline circulation. So we can't really look at one scale here in isolation of the other, but we can sometimes find paradigms for the flow field that are governed by just a few of those terms in those big gory equations I had previously. Okay, and so the way we do this mathematically, and I'm not going to go into all of the terms and show you they're small, but I just want to point out just one more preliminary concept before we get into the equations and see how we can whittle them down to some processes that are easy to understand. We can scale the terms in these equations just by remembering what these calculus terms mean. So derivative of say, the velocity, east-west velocity here. So the rate of change of east-west velocity in time kind of scales with the size of that flow field divided by the time scale over which that operates. So if you think about an eddy, you might think about, the edge of the eddy is about 1 metre per second in the ocean, and that eddy persists for weeks or months. So you can start to estimate the size of this acceleration term by recognising those two scales, the velocity scale and the time scale. And likewise, second derivatives in time scale as, it's not u squared on t squared, it's just u on t squared. Terms like, whatever term you like, a term like u, dv dx or something like that, scales as, the horizontal velocity we think of as being, approximately the same in both east, west, north, south sense. So it's scales as about u squared all over the length scale L for the flow. So any of these terms in those equations that I started with a couple of slides ago, all these terms here, we can start to think about how big they are. And in particular, a lot of these terms, these nonlinear terms here, tend to be very much smaller than terms like the rotation force and the pressure force at large scales. Okay, this is where I apologise at this point because I'm going to grab some scratchy handwritten notes and put them up on the board. And you do not have to read every bit of this text here because it's hard to read anyway, but I will point to the bits we need. And this was, I was going to take the primer and start redoing all of the notes that I've got on this, and it just would have taken me all weekend. I didn't have that time. So here are the equations again. So this is where I'm asking you to be a little bit adaptable. These are the momentum equations, exactly the same equations that I had previously in 3 dimensions, but now written in vector notation. So this is the 3-dimensional vector for u. This is the rotation term, pressure force. These are body forces, and it's really only gravity that matters here, and then frictional terms and so on. And here's the continuity equation, or the conservation of mass equation for incompressible flow. And the scaling arguments I've already referred to, we'll just go through one of these, and then the rest will sort of drop out in no time at all. Think about, say, a flow in a gyre. Length scale's about 1,000 kilometres. The Atlantic and the Pacific are many thousands of kilometres, so is the Indian Ocean. The depth scale's about 4 kilometres for the flow in a sort of constant density, large scale gyre. So you could take the vertical scales about 1,000 metres. And then if you want to think back to the early oceanographers, right, they didn't know what the vertical velocity scale was at all. They wouldn't have been able to, it's a very, very slow rate for much of the ocean or the atmosphere. So to get the vertical velocity scale, they would have had to have, this is the best way to do it actually, not to go and try to make a micro sensor of velocity in the ocean. You're much better off acknowledging via the continuity equation that any velocity scale in the vertical divided by the depth scale you're looking at scales with a term like u over L. Okay, so the change of the velocity field u over the length scale that's occurring over. And so you can get an estimate for how big the vertical velocity is for a large-scale eddy in the atmosphere or a large-scale eddy in the ocean or a gyre from that kind of argument. Plug in all the numbers that you know. For example, go to an eddy, maybe 100 k's in width, velocity field of 1 metre per second, some sort of depth scale, say 1,000 metres deep, and you can drop out the vertical velocity in the broadest order of magnitude sense. And so if we go back to this full glory equation, this is the full 3-dimensional equation for momentum in the vertical sense. These are all the terms. This is now looking much more like the notes you had for the primer. Even rotations thrown in here. All of these terms, if you look at how big they are and do the algebra, you can see their terms like compared to gravity at 10 metres per second squared. All these terms are many orders of magnitude. The nonlinear terms here are about 12 orders of magnitude smaller. The rotation term is 1 million times smaller. And so all the terms there drop out to being, for these large scales of flow in the ocean and the atmosphere, they drop out to being very small, and you're left with the first of my little dot points in the, hydrostatic balance had to be achieved. We're there at 10 minutes into the hour, or really 1:15. Here's the hydrostatic balance. It just basically tells you for any parcel of water or air, if the flow is happening slow enough, then this parcel has two major forces acting on it. In the vertical, it's got gravity. If gravity had its way, it would be sending the water parcel down to the bottom of the ocean. But it can't do that because actually opposing that is the pressure force. So pressure is always trying to, and we'll come back to pressure in the horizontal sense a bit later on, but the pressure force is always trying to send water or air from high pressure to low pressure, and whether that's horizontal or vertical. In this case, the pressure force, you know that as you dive into the ocean, your ears start to hurt. So as you go down, pressure gets higher. So pressure force wants to push the water up, gravity wants to push the water down, and this balance holds for many, many types of ocean atmospheric flow that you'll hear about this week. So this is the hydrostatic balance. It works to many significant figures. If you look back to the orders of magnitude that I just went through, the pressure, though, does depend on, just quickly before I get off this balance, the pressure is dependent on X and Y, okay? So it's not as simple, you can't just sort of integrate this out with ease. It's a bit easier if the density is constant, then you can take density over to this side, integrate in depth, and you get the pressure at any X, Y, so anywhere in space and time is, I don't have I should put a little schematic here, but basically if, you already see this marker from here, it's far away for you guys at the back. But, so here's the sea level with a zeta here. So sea level, depending on position in space and time. If you've got a constant density ocean, then at any depth Z, you can relate the pressure at depth Z basically to the depth you're at plus any variations due to the sea surface moving about. And we'll come back to that equation a bit later on. It works for a constant density ocean. And the ocean, if you think about the numbers you look at for the density of the ocean, it varies from potential density varies from 1,023 kilograms per meter cubed up to 1,027. So it's kind of constant, it's to first order. But there are variations that are very important we'll come back to. So there's the hydrostatic balance. Now you can do the same thing I just did, identically the same thing, but now in the horizontal sense. Again, apologies for these scratchy handwritten notes here, but this is again exactly, well, not quite exactly, the rotation terms are written a bit differently here. But this is the equations that you've got in your primer, the ones that I started off with. This is now the momentum equations in the east-west and north-south sense. Here, first, the east-west sense. Exactly the same process. Go and do the scaling argument for all of these terms. U du dx goes as u squared on L and so on. Each of these terms can be scaled and you get orders of magnitude like 10 to the minus 7 to 10 to the minus 8. We won't worry about the pressure term. The only one that gets close to, say, order 1 is, it's this rotation term here. So this, the so-called Coriolis term, and I know that rotation effects were in the primer again, so I do hope that you guys read or watched the primer notes. So the rotation term, in effect, if you think about the Earth rotating, right, so the rotation term in the vertical just gets absorbed into gravity in effect, right? Okay, so if you think about the Earth rotating. But in the horizontal sense, the rotation term isn't absorbed into gravity. It's actually a real term that matters for any flow that persists of the order of half a day or more, okay? So quarter of a day or more. So rotation, and that sort of makes sense. The Earth's rotating once per day, right? So rotation matters in the horizontal for these time scales, like for eddies, like for the gyres and so on, like for weather systems in the atmosphere. So all these terms, the nice thing is for large-scale motion in either the ocean or the atmosphere, all of these terms to 1% accuracy go, and we're just left with the geostrophic equations. And sorry, this looks a bit, for the experts in the room, they're saying, hang on, twice the rotation rate of the Earth, because this is 90 minus latitude here. When I did this, it was all done by first principles in these notes, where we had all 9 terms in the rotation vector in the 3 senses of east, west, north, south, and vertical. Anyway, who's seen these? Give me an idea. Who's seen these geostrophic equations before in the room? Oh my God, what am I doing dwelling on this? You all seen them? I thought for some of you this is new. This is so lovely to know that you've all seen this before then. So it's just, F times V on this top equation there, balanced by the pressure term, and then minus FU on the bottom. Okay, so here's this explanation of my horrible notation for the Coriolis parameter. Let's just take it as twice omega being the rotation rate of the Earth, which is 2 pi radians per day, if you think about it. So you never need to memorize that. It's always just 2 pi radians per day. And then sine of the latitude, lambda, or cos of this funny angle I had in here. So geostrophic flow is just basically the flow that arises when you have a large-scale pressure gradient. Let's get some pictures instead of words. Here's geostrophy for a raised sea level or a high-pressure system in the atmosphere, whichever you like. So this could be a warm core eddy in the ocean or a high in the atmosphere. Basically, the forces at play here that are dominating are the pressure gradient force, which wants to send water or air away from the high to the edges of that high, and the rotational force, which actually tends to want to oppose that and send the water back into the center of this gyre or the center of this weather system. And the resultant flow is actually at right angles, and I'll show you. You can prove this. It's sort of a trivial consequence of the geostrophic equations that I'll show in a second. So here's the geostrophic flow. It's around lines of constant sea level elevation or isobars or lines of constant pressure in the atmosphere. Just to quickly show that the flow does follow pressure contours. Oh, sorry, skip down just to this momentarily. So it's the same. I've said it's for the highs and lows in the weather systems, or equally eddies in the ocean, or the gyres even. Basically, the geostrophic flow. Here are the equations that I had up previously, with rotation terms being balanced by pressure. You can multiply this first equation by U and this one by V, and then add them together, and you can see the FUVs cancel on both sides, and you can just show that the velocity vector is perpendicular to the pressure gradient, basically. So the velocity field runs along constant lines of pressure or constant lines of sea level. So when you look at a weather map, whether you're a sailor wanting to understand the winds, or a surfer or whatever, you can, or just to know whether it's going to be a cold day or here's a cold front that's just come through. You can basically take these pressure lines in the atmosphere as defining the flow field to first order. Equally, when you look at a satellite image from space of the surface, this is a sea surface height or sea surface elevation plot. These eddies, you can backtrack the sort of flow field by remembering that, under geostrophy, the flow runs along lines of constant pressure. So these cold core eddies would circulate you have to go via hemisphere, and a cyclonic eddy here, this low in the northern hemisphere would rotate in one sense, opposite sense for the raised sea level just here, and the flow, if you go across the Gulf Stream here off the US, the flow across this Gulf Stream, you can again track it just with geostrophy. The sea level is rising across that front from inshore to offshore, and that drives a flow perpendicular to the gradient of pressure. Yeah.
Sorry, Matt, are the units of those height anomalies in meters?
This is not meters here. This is centimeters, right? Oh, centimeters. Yeah. Sorry. Yeah. So across the gradient. Good questions. That's the gradient across one of these currents is about. You look at that's typically about a metre of sea level. So the ocean sea level elevations are very subtle but detectable from space, and a metre gradient across this current gives you the Gulf Stream. Typically, maybe up to a metre across or half a metre across some of these eddies. It's about 1.5 metres across the ACC, I think. So these are subtle variations in sea level, but they're really important for driving the geostrophic flow patterns. And you can go to a global plot of this, and you can more or less see all of the ocean currents, or a global weather map. Andy's weather map, or the lovely animation that he showed, you could almost visualize what the pressure systems would be from that flow field that you were seeing. Okay, now there's one thing I skipped over quickly. I just want to show you one kind of nice consequence that drops out of the geostrophic and hydrostatic relationships when the density is constant. So this is the Taylor-Proudman theorem. It just applies to a hydrostatic flow that's in geostrophic balance. If the fluid is at constant density, you can just do a bit of algebra here. So here's the geostrophic equations here, 1 and 2. Here's the hydrostatic balance at 3 and the conservation of mass at 4. You can just take, differentiate through in y for equation 1 and through in x in equation 2. Sorry, strike that. Differentiate through in x and y for equation 3. And then, of course, gravity doesn't vary in the horizontal sense in any meaningful way. And so these two terms here are identically 0. And then you can plug that into the equations 1 and 2. If you differentiate these ones through in z, you can show that if you didn't follow all the algebra there, don't worry, just come back to me now for a moment and just think about this. If the fluid is constant density and it's in geostrophic and hydrostatic balance, then the shear of the flow or is 0, or equivalently, there are no gradients in the vertical of the horizontal flow field. I'll show you a diagram of this in a minute. So mathematically, U and V have no gradients in depth, which means they're constant at depth, with depth. You can also show that the velocity field in the vertical has to be 0 just through the continuity equation. And so, again, if I lost you for that bit of algebra, I didn't want to go through the mathematics of how you get there, but it's a very simple consequence of just fiddling around with those 4 equations. So if it's geostrophic and hydrostatic, which actually applies to many of the large-scale flows in the ocean or the atmosphere, and the density is constant, that obviously doesn't apply, but I'll come back to that in a second, then the flow tends to sense obstacles at great depth. This is kind of magic, you know. Go to a rotating tank or some part of the ocean where density is constant. Look at the flow over a seamount that's way below the depth of the surface, and the water column right through up to the surface feels that bit of topography. To me, this is crazy, right? Think about it. But why would this fluid at the surface care about the seamount down below? If the density is constant, and the two constraints I had previously, hydrostatic flow and geostrophic flow, are met for many large-scale flows, then you'll see a signature of the abyssal seamount right up to the surface. Now, of course, the density in the ocean is not constant, but let's have a look at this. Is just output from a model I ran too long ago, and it's showing the flow fields at about 70 meters depth. I wanted to get below the Ekman layer, and I'll talk about Ekman flow a bit later on. This is just the flow field at 70 meters depth, but all these topographic features here that I've highlighted, most of them are at about 1,000 to 3,000 meters depth. Certainly this sort of East Pacific rise through here, the Campbell Plateau is at about 1,000 meters. Now, think about the ocean's density structure. The ocean's density in the Southern Ocean, if you look through a profile or a vertical section of the ocean, let's pretend this is now Antarctica here. You see, if I did density lines here, you see a lot of density lines. This is the tropics up here with the sun beating down. So in the tropics, there's a lot of warming of the surface. You get a lot of stratification here. So my density constant idea is out here. So density is not at all constant, okay, up here in the tropics. Now in the Southern Ocean, it's not constant either. There are gradients of density from the top to the bottom, but much weaker density gradients. It's under a kilogram per meter cubed over the Southern Ocean. It's more here. But the flow here, you can see the flow here in the tropics where there's more stratification. The surface flow doesn't really care too much about the bathymetry here. But in the Southern Ocean, you can see this flow field's being cranked around in a big way by the Campbell Plateau. So the surface flow field is sensing the bathymetry well above where the bathymetry is. So this magical relationship that seemed to drop out that you wouldn't think would hold for the oceans or the atmosphere. You can see kind of quasi-Taylor columns if you look at these systems. Okay, so I've covered these bits. Okay, so Yeah, I got the sense the room's hanging with me. I'm appreciating this. It's getting to the edge of your concentration space, you know that. This is the time you're about to switch off and start thinking about the weekend or what are you doing tomorrow. Okay, so if you look through the dot points I'm going to cover, I think I'm about halfway there, and it's technically halfway through my lecture as well, so that's good. Okay, so the next thing I'm going to talk about is thermal wind. Again, I don't want to go through all the maths from first principles. It is covered in those books very beautifully, but the thermal wind equations drop out when we no longer talk about density being constant. So this Taylor-Proudman idea was for a constant density ocean or atmosphere. We now have density varying in space and time, but again we start off with geostrophy and we start with the hydrostatic relationship, and you can build up what are called the thermal wind equations just by simply manipulating these equations, which I'll show in a minute. I already talked about the sea level of the ocean having these undulations that drive geostrophic flow. Equally, pressure surfaces in the atmosphere have these spatial variations that determine geostrophic flow. All you need to do is take the z derivative of both the geostrophic equations, and then, because the pressure field's well enough behaved to swap the order of differentiation in x and z, we can take these as being equivalent, and then using the hydrostatic relationship, we can relate the pressure gradients in depth with the density gradient, with the density itself and g. And so basically, here, this is in a sense geostrophy differentiated in the vertical, and we bring in the hydrostatic relationship to replace dp dz here. And then, so we end up with an equation that relates the vertical shear of the flow. So this is the vertical rate of change, basically the velocity v and u, being related to the density in the horizontal sense. But it's like geostrophy, it's the flow field in the north-south sense is related to the density gradient in the east-west sense. And equally, the flow field in the east-west sense is related to the density in the north-south sense. And this is all because of the Earth's rotation effects. Okay, so these are thermal winds. Why are they called thermal wind equations when we're talking about, say, ocean flows? Well, they first came about, meteorologists tend to lead oceanographers in understanding the fluid dynamics because the field's like 30, 40, 50 years old, or at least. They got there first with this, and so it can define, say, the wind field with a front in the atmosphere, a thermal front coming through. You can use this set of equations to describe the flow field as you go through the front in the vertical sense. I'm used to thinking about the ocean, so just to show you what I mean by this, so memorize these equations here. Okay, the vertical shear, you could take rho and the Coriolis parameter outside the front here for many applications. Okay, I didn't get to put this in my notes, but the density gradients here in space matter a lot. These vertical ones, typically you can take them out the front. It's to do with an approximation for flow in the ocean. I'm sure we'll come back to the Busson-esque relationship can take this density parameter out the front here. But you can basically relate the shear of the vertical profile of horizontal velocity to the horizontal gradient in density. It's a mouthful, so let's look at it in a diagram. The equivalent thing here would be if a ship tracks across this bit of ocean, it takes a profile of temperature salinity measurements here, another profile of temperature salinity measurements here. It's got a density structure at both stations, and the way oceanographers will build up the flow field through that section, that we don't know anything about the data between the two stations, so all we've done is taken measurements here and here, so we've got no knowledge of the stuff in between, but we can look at the density structure across that section, and if we assume a depth of no motion, you can imagine integrating from that depth of no motion up through the water column with this relationship here. So if you integrate this with depth, you can build up your flow field u and v from a starting value of 0 at the depth of no motion. As you move through the water column, you progressively build up knowledge of your flow field from the density gradients. And so the first bit of seagoing oceanography I did was to go off Sydney on a boat. The guy running the cruise got horribly seasick, and the rest of us just had to, actually everybody but 2 people on the boat I think got horribly seasick. We went off Sydney, so here's the Opera House of Sydney. when I was in Sydney, and it was a terribly challenging field trip. We had one day, and we had to get to the East Australia Current, which was miles offshore, and we barely got to the start of it, and took one TS section here, and then a second TS section as far as the crew and everybody could handle the rough conditions. And then we built up knowledge of that section, the flow field in and out of the page, from these density gradients across this section. And we had to assume a depth of no motion here where U and V were 0, and then you can integrate up. That was the exciting thing we had to do when we got back onto land, was to plug the T and S values into the equation of state, get a density value, these two guys here, get a density value, and then integrate from the depth of no motion up through the water column to get a flow field. And we proved to ourselves we made it to the Australia Current because the flow was going poleward. It was a lot of work for one section with two profiles of data. That's how oceanography used to be done, though, and that's the kind of thing that we had to rely on years ago before Argo floats and so on, just to take these profiles through the ocean, build up a knowledge of the flow field from the density, knowing that it was kind of basically geostrophic with some and hydrostatic. So here's an example. You might cut through, say, the ACC here and look at this is now density sigma 0, and you could basically build up an idea of the flow field under these assumptions. You won't quite get the right answer. You'll get an answer under those two assumptions of geostrophy and hydrostatic flow being about right. Okay, so the last thing I'm going to cover, it's going to take a fair bit of the remaining, I might only need 15 or 20 minutes for this, so we might finish early even. The last thing I'm going to cover is wind-driven flow. So far, if you think back to the equations I had at the very start, here they are. Just to sum up where we got to, basically I showed for this third equation here, in the vertical sense, the two things that matter the most for almost all applications are just gravity and the pressure gradient term. Who knows, can people think about when this is going to break down, my hydrostatic approximation? I think a lot of people will know this. Got some answers? Yeah, I can see the answer. You all know it, sorry. Convection in the atmosphere of the ocean, where the flow is way too rapid in the vertical to neglect some of these other terms. And so that was the first main result to drop out. The next one was that, basically geostrophy rules in large-scale flow for the ocean and the atmosphere. So these two terms here dominate. But we haven't talked at all about the frictional terms on the right-hand side here. And so that's what's going to take up the last 15 minutes or so of this class. When you have wind blowing over the ocean, or equally the atmosphere dragging along some vegetation, you'll generate a boundary layer that is where this frictional term in the vertical sense, so the frictional shear, say, across the ocean interface into the wind zone here, that frictional shear is a term that actually dominates the balance of flow in either the ocean or the atmosphere. And so I'll come back to Ekman in a second. In these equations, it's actually these terms here. Okay, these last terms, the vertical shear of velocity the vertical shear of horizontal flow in a way that dominates. We won't talk about these lateral shear terms in this part. It's the vertical shear that matters. So let's just come back to Ekman for a moment. I'm going to show a couple of other guys later on too. There's a story that's going to precede Andrew's talk that I thought was worth saying. It was going to be part of my lecture, and I'm happy to drop the Sverdrup balance, but I need to tell you about Sverdrup and Stommel before I drop off the class at the very end there. But this fellow, he was amazing actually. The Ekman equations and all the Ekman relationships that I'm about to go through, he nailed in his PhD thesis. So, I mean, that's a high point for your career. Where do you go from there? To have flow fields and the Ekman layer depth, the Ekman flow, the Ekman transport. How many things are named after this fellow? But he basically, and here we are, a situation where, Nansen, these are all big names, asked Bjerknes to let one of his students make a theoretical study of the influence of the Earth's rotation on wind-driven currents. And it was based on some observations, actually, to start with, of sea ice. The observation was that when the wind blew over sea ice, again, this is a frictional shear of the wind on the ice. The ice wasn't going with the wind. It was heading off in the northern hemisphere to the right a little bit. And this sparked, I love this Nansen just, so it's like me going to Andy Hogg and saying, can you get your student to do this calculation? So it's, somehow it seems a funny setup that all these big names in oceanography were there thinking about this problem, and this fellow nailed it for his PhD. So I think I look back at a lot of the things you do during your PhD are really, that's when your mind's fresh and you've got no preconceived ideas, and he came and nailed this problem as a graduate student. And I'm going to go through to start with the depth integrated response to a shear. That's a much easier mathematical problem than this Ekman spiral that I'll get onto afterwards. Okay. So the assumptions that Ekman made in his PhD thesis were as follows: that the flow was pretty much steady. So we had a steady state. So the wind blew on the ocean, but it blew for long enough that you kind of the acceleration terms are pretty much negligible. So it's like a steady state setup where the vertical shear from the wind, so these last two terms here, so just the first two equations too, just these east, west and north, south equations, the vertical shear was important. The pressure terms are important. So we have the pressure terms not being deleted, ignored. Rotation still matters, but it's sort of steady enough flow. And it was in the primer again, but these terms for the velocity, for the vertical shear, can be written as a sort of a wind stress divided by, in this case, for a constant depth ocean, h, and densities in there as well. So effectively, all these are going to go to zero. On the left-hand side, we're just left with rotation. On the right-hand side, pressure plus this vertical shear. And so back to my scratchy notes. Apologies again. These guys go to zero. As I just said, rotation stays, so does the pressure gradient terms, and then we have these frictional terms in the vertical sense. The pressure, if the density is constant, the pressure terms here can be replaced. Remember, ages ago I had density constant. We can write pressure as, basically rho g zeta minus rho g z, if density is constant. So if density is constant, you can actually replace these pressure gradient terms with the gradients of sea level for the ocean. Now, if we depth integrate these equations here, or when Ekman did this depth integration, it drops out really nicely for depth integrated flow. I'll just go through that now. Depth integrate these equations and then average over the total depth of the ocean. So right from the surface down to some bottom. Here's what the equations look like. The rotation terms on the left-hand side look familiar, pressure gradient terms, and then in the depth integrated sense, you've got a stress at the surface minus a stress at the bottom. And we'll take the ocean to be deep enough that these guys go to sort of a small value or zero, and you're left just with these equations here, which can be simply split up into, the flow field averaged in the vertical can be split up into a geostrophic component and an Ekman component. And the geostrophic component then is just given by the familiar terms we had previously, and the Ekman component looks like this set of equations below. So they look geostrophic in their nature, if you like. The north-south Ekman velocity scales with the east-west wind stress, and the east-west velocity with the north-south wind stress. So you can see it's a very similar, by analogy in some sense with geostrophy, the wind stress is trying to create a flow field in this direction, but rotation is kicking in and actually insisting that the flow is perpendicular to that wind stress field. Just like in geostrophy, the pressure gradient wants a flow that's in this sense, and the resulting steady state flow is along lines of constant pressure. Okay, so what does that look like? If you have this is for the northern hemisphere, if you've got a wind blowing, say, a southerly off California, so this southerly wind is going in this sense, then the Ekman transport will be onshore if you're sitting off California. Or if you have, say, an onshore breeze, same, at the coast of California, then you'll have an alongshore Ekman velocity down, the flow heading off down the coast. And I've got to emphasize, this is for the depth integrated flow. So I'm going to come back to this spiral in a little bit. Probably a lot of you have seen this Ekman spiral in different classes you've done, but this is the depth integrated flow that I'm talking about. It drops out really nicely. I didn't go back and look at Ekman's thesis, but I presume it was somewhere in the early part. Just look at this in the depth integrated sense to start with. I might just quickly skip down past this bit and just show you, some of the consequences of that result about the Ekman transport being perpendicular to the wind field. So a lot of people live on the eastern seaboard here, I presume. I know there are lots of Melbourne people and people from overseas as well, so just bear with me for a moment. Just imagine you're up in Sydney and a southerly wind comes up, so this wind is into the page. What that southerly wind does, initially it creates some drag on the ocean. It creates some wind waves that obviously propagate with the wind. If the wind blows for long enough, it needs to blow for a day or two, right, for the rotation effects to kick in. If the wind blows for long enough, there's an Ekman transport that actually becomes strong enough that it sends a lot of this surface water towards the coast. And the water's got nowhere to go, so it actually starts to pile up at the coast. And this is Ekman transport in action. Anybody who swims at Sydney every day, take note, southerly winds, you'll notice a slightly higher sea level. There's a tidal signal that you've got to filter out. It's pretty hard to do because the tidal signal is a couple of meters during the spring tides, right? But I promise you, on average, you'll notice after strong southerlies, there can be a couple more meters of sea level, right? For a really strong storm surge, this can be a couple more meters. So it needs to blow, the longer it blows for, the bigger this effect. You get an Ekman transport onshore. You do eventually get a geostrophic adjustment. So when the sea level raises up like this, there's a sea level gradient and you get a geostrophic adjustment that has the flow below the Ekman layer coming in the same direction as the wind field. And all of this Ekman transport, I'll talk about this in a minute, is actually trapped, even though we covered it for the depth average right to the bottom of the ocean. I'll show in a minute that all of this flow is actually due to frictional effects. It's all bounded in an upper layer of about 30, 40 meters depth. Okay, so that's a storm surge. Just quickly before I get off storm surges, these can be incredible because now you've got to see you're flexible listeners, because I've got the coast now the other way around. Coast was over here before, now it's over here. So we're looking down the coast of New South Wales, for example, and so here's a storm surge. So again, I've got the winds now coming out of the page. Ekman transport goes onshore. Here's the tide range. So here's the extra amount due to the Ekman transport, this storm surge. But on top of that, these wind systems that I just spoke about, so a southerly for the New South Wales coast, it does tend to be accompanied by a big sea state, so swells of 3-4 meters. There's a decent storm surge happening at the moment with a low off the southern Tasman, and that creates extra inundation of the coast. It can be incredibly devastating for coastal communities. A tropical cyclone, this is just off Queensland, but a tropical cyclone hitting a low-lying region of the world can do huge amounts of damage. And it's not just the winds directly creating swell, it's also a storm surge. So if this low sits there for a long amount of time, that does a lot more damage than if it's moving about, okay? Because this Ekman transport spins up into a steady state with a steady forcing. You need a steady forcing. So if this sits there for a long time, you get a much more devastating storm surge than if it's moving up the coast or moving around. The worst sort of event could be if it comes. There was a cyclone that bullseyed just, I think it was Yassi, I guess, just north of or south of Cairns. I think it was, I forget which. It just didn't quite hit Cairns at the right. New Orleans, Katrina hit New Orleans at the worst spot to create a storm surge and to create big damage there. But this low coming in, Yassi came in this sense, and so the Ekman transport, was developed nicely for this cyclone. All the swell was coming in the worst place to be, because the swell is coming onto the coast here. If you're up here to the north of the eye of the cyclone, it's a little bit better because there's not a swell coming in the same position as the storm surge. The storm surge is happening right across here, but the big swell front is on the south side of that eye of the storm. This is getting into coastal inundation, but it's driven by Ekman dynamics, worked out over 100 years ago. Okay, so I'll just go back up, and the last thing I've got to do mathematically, and I'm not going to go through all the algebra, just going to convince you guys it can be done. So the last thing I'm going to cover is just this Ekman layer in the vertical sense, to get more of an understanding about how things vary in the vertical sense. And so I'm sure by now you know all the momentum equations, back to front, these ones up here. What I'm doing now is I'm going to start with I'm forgetting about geostrophy. I'm just going to think about a balance between the rotational acceleration term and this vertical shear term. Unfortunately, I'm sorry, but this, the vertical viscosity here is going to be replaced by the letter A, which is not a good choice of symbol, but you guys are used to me doing this. I'm changing the symbols around, and all the rest is the same. So here's the Ekman equations. Okay, the rotation terms on the left-hand side. On the right-hand side, this vertical shear, A is the vertical viscosity, okay? All right, so what are the assumptions? Basically steady flow, rotation, and friction in the vertical sense are dominating the balance here. It's a steady state setup. Basically, this is a coupled set of ordinary differential equations of second order. And if you remember your first year maths, you need to have two boundary conditions to solve these, two each for U and V. And when we have those, U and V tend to 0 as Z goes infinitely deep, or in the atmosphere, if Z goes away from the boundary far enough, the flow field or the wind would go to 0. And then across the other set of boundary conditions is that this stress across the ocean's interface, or from the vegetation to the atmosphere, that there's a sort of continuous stress across that interface. And so this is described as by these equations here, that the shear in the wind or the ocean current multiplied by the viscosity coefficient density goes as this wind stress at the surface of the ocean or at the surface of vegetation. So these are the boundary conditions at the surface of the ocean, say where Z equals 0, or the base of the atmosphere, and these are the boundary conditions as you move away from the Ekman layer. Now, you can do this solution of these equations in so many different ways, right? In these notes, I did it with a complex notation system and combined to get one variable. But there's other ways. The Benoit-Cushman-Rosen book solves these equations differently again. And so you can basically, with these equations, you can basically combine them into one single equation, a second order linear ODE, by adding the first equation to the second multiplied by I, where I is the complex number. And so you can replace U and V with this single sort of velocity variable phi in complex notation. This has very simple, this is like a second derivative in Z with the variable, so it's A, although A is the vertical viscosity, sorry, E to the square root of this constant here times Z plus, a second term, E to the minus square root of that term Z. So think about it, go back from here to here, differentiate this twice, right? Differentiate this guy twice and add this other term, you'd get to 0, right? So you can see that that solution makes sense. And in here, again, my apologies, A refers to the viscosity in the vertical sense, F is the rotation parameter, and it turns out that this will help define, later on you'll see that this defines the depth of these Ekman flows, because there's like an E-folding decay of the flow field with depth, and the E-folding decay distance goes as F over the viscosity coefficient, or the other viscosity coefficient over F. Okay, so we can replace, we can define this Ekman layer depth effectively as twice the viscosity coefficient over F, all to the power of a half, and then forget about this algebra. I mean, well, you don't forget about it. The algebra is sort of straightforward, kind of first year calculus, and you get a skip down to the equations for U and V. The flow field in the east-west sense scales as a bunch of constants, including this Ekman layer depth here, times the wind stress in the north-south sense, okay, perpendicular. And here's this exponential, Z is positive upwards, okay, so downwards is negative. E to the, effectively a negative number in depth over the Ekman layer depth, and then this cosine function with a sort of phase offset of 45 degrees. I'm going to show you a plot. This is a bunch of mathematical terms. The best thing for me to do is show you a plot of this, right? Okay, so, and V has a similar format. If you plot this in three-dimensional space, you just get this, right? So, and it makes sense. If you look through the vertical sense, the vector is dropping off with an e-folding distance of this delta term here, right? That's the e-folding distance in the vertical sense, delta being twice the viscosity coefficient over F. Right, so this breaks down on the equator where F is 0. So there's a decay in the flow field with depth. And at the surface, where Z equals 0, just back to the equation, where Z equals 0, there's an offset of 45 degrees. So when the wind blows, where Z equals 0, this is obviously 1, right? But there's an offset of 45 degrees in this cosine and sine function here. So bottom line is that Ekman discovered that the surface flow is at 45 degrees to the wind, and to the right in the northern hemisphere, to the left in the southern hemisphere. All of these, this here is just simply plotted by this. And if you depth integrate it, you get this 90-degree transport to the left or right of the winds, whichever hemisphere you're in. Okay, so I'm not going to, you can go through and do exactly what I did. So same equations for the depth integrated transport. And you can show that that the flow field is at right angles. We already did that previously with a different starting point, okay? So I'm not going to do that again. I've covered those applications. I didn't cover upwelling though. So the converse situation of my storm surge is that you get a wind coming from the north. And this is very counterintuitive in summer. Anybody who's been swimming on a summer's day on the eastern seaboard might remember this. You go down northerly winds generally are warm. Okay, so nor'easters are a bit cooler coming off the ocean, but a northerly wind is often accompanied by very hot weather. And if this blows for a while, for 3 or 4 days, the amount of Ekman transport heading offshore is significant. It does lower the sea level even, detectably, if it's a strong enough event. And you get a compensating upwelling of very cold, nutrient-rich water. You do even get a geostrophic adjustment, again in the direction of the wind. But these temperatures, the coldest temperatures you get in Sydney, for example, don't occur in winter because these upwelling events can get the water down to about 12 degrees, 13 degrees, right in the middle of summer with a big enough event. Why summer? Because nor'easters can be prevailing in summer. They're not prevailing at all in winter. So you can get a week-long northeasterly wind breeze that basically sends a lot of water offshore and the cold water comes up to replace it. Here's an image of that exact same process at play off California. So going to the west coast, so it's also a northerly wind. It's counterintuitive, but if the West Australians don't have this effect. I can't give this class over in Perth and say what I just said, because actually in West Australia, a southerly wind creates upwelling, right? So it's a cold wind creating upwelling. So it depends which coast you're on. You get less of a shock, put it that way, if you're in West Australia. A warm northerly, onshore winds, warmer ocean waters. Off California, not as counterintuitive for them, cold northerly wind. Ekman transport to the right, so it heads offshore. That brings a lot of cold water up to the surface. And you can see it scales very much with chlorophyll. So here's ocean colour here. And it's incredible how much the ocean colour scales with the temperature in this plot. All these little features and filaments you can see in ocean colour as well as in SST. That's showing you that this water is not just cold, it's incredibly nutrient rich, and it's creating an algal bloom wherever the nutrients are high in concentrations. So it's important for fisheries and so on to track these upwelling events. Okay, it's 5 minutes to our afternoon tea. Now I can sense, I had a sort of halfway break and everybody was alert. I can see just levels of fatigue kicking in. So I might finish up there. Bear with me 2 or 3 minutes. Andrew's going to come back to this Ferdrup balance on Wednesday. And I mean, the basics of this Ferdrup balance are, just to lead a little bit into where Andrew's going with this, is that the winds over the planet tend to be westerly at, it's amazing, Jupiter's got more of these banded wind fields than we do over the Earth. But we have a couple of them, westerlies at mid-latitudes, and then the trade winds at along the tropics, and that sets up these Ekman transport flows that I've been talking about at the largest scale. So just coming into this diagram here, this is just plotting wind vectors over the globe. If you think about the transport For Ekman, it's to the left of the wind in the southern hemisphere, so you get a convergence in these gyres from the Ekman transport. Right? Once these gyres build up to a sort of steady state height, geostrophy kicks in, and the geostrophic flow in response to this is around lines of constant pressure. So you get these large-scale anticyclones in the ocean with flow going around the pressure systems in a geostrophic adjustment, with water poleward at the western boundary currents and equator at the eastern boundaries. But as Andrew will tell you in a couple of days' time, the flow field here, it's so slow that to conserve the vorticity, so the wind is saying, pumping this vorticity into the system at a significant rate. The relative vorticity, so the spin of these gyres, is not nearly enough to keep that in a sort of vorticity balance. You need actually the planetary vorticity, so F to kick in, and it turns out that, and Sverdrup worked this out, that in the interior of the gyre, the flow is equatorward, and it's actually only in the western boundary currents where you get this poleward flow. And so there's a lot of asymmetry across the gyres. I'm going to leave that to Andrew, but just to finish up, I love this story. It's just worth telling. So here's the solution that Sverdrup worked out. Sverdrup was a Norwegian oceanographer. Here's his bio. Really one of the most famous things was this relationship that Andrew will cover on Wednesday. But I love this bit of the story, that Henry Stommel turned up and asked him to do a PhD. Hal, Professor Sverdrup, please will you take me on as your PhD student? He was denied admission to the graduate school at Scripps Institute of Oceanography. So Hal Sverdrup said to him, sorry, I can't take you on. You're not a good enough student. So what Henry Stommel went and did is so Sverdrup worked out the interior gyre and Henry Stommel worked out the western boundary current that Andrew will tell you more about. So the moral to the end of this lecture is that when your supervisor says to you, you can't do something or they're not going to take you on, go and work out everything that they've been doing and prove them that you're an outstanding. And Stommel never got a PhD. So is there a moral to that story? Do you need a PhD? No, you need a PhD. Henry Stommel never got a PhD, and he went and redefined oceanography at in so many problems, not just gyres, but also the overturning circulation. And this is an inspiration for any PhD student, I think. Okay, thanks a lot.